All right, so here we're being asked to propose a mechanism for the conversion of this starting material plus HCl into this product. Now, it already tells us that there's a rearrangement. So it says it yields a rearranged product. So that gives us a little hint that we might be looking at some sort of a hydride shift or a methyl shift. So let's just see what happens. Well, we have a double bond and we have HCl. So we should immediately be thinking about the addition of HCl across that double bond, and that brings to mind the formation of a carbocation. So this first mechanism should be very familiar, or the first part of the mechanism, I should say. And we can draw these curved arrows like so. So we draw the double bond coming up to pull off the proton, double bond being the nucleophile, the proton here being the electrophile, and then chlorine leaving a Cl minus. And this first step yields this carbocation. So why did we form this carbocation and not the carbocation down here? So why did we not form this carbocation? And the answer is that this carbocation is more stable because it's a tertiary carbocation. So now whenever we're looking at proposing a mechanism for a reaction, it's always a good idea not only to go forward, so we weren't really thinking about the product here when we were going forward in the forward direction. We just said, okay, we have a double bond and we have HCl. Let's just see what happens if we protonate that double bond and give, and what sort of a carbocation do we get? And then maybe we can think about how to get to the product from here. And so let's now start looking at where we're going. We have this carbocation, which is probably the likely first thing to happen. And now notice that we have this carbon with two methyls here, this isopropyl group sticking off, and that looks a lot like this. I should draw that in a different color. That looks a lot like this little arrangement of atoms here. So we have a carbon with two methyls attached. We have a carbon here with two methyls attached. And the chloride ends up on this carbon. So there's a hydrogen here, and we need to replace this hydrogen with a chloride. So we have a carbocation right next door, so this should bring to mind a hydride shift. So if we shift that hydride over to that carbocation, we will get a new carbocation. So we'll get a new carbocation here, and that hydride moved over to essentially quench this carbocation. And now we see that we can get to our product very easily by adding Cl minus to the new carbocation. So Cl minus adds there, and that's in a single step we can get from this tertiary carbocation to our product. Now, you may be wondering, well, what's the driving force for this? We formed a stable carbocation here, so why not chloride? Why does chloride not add to this carbocation and give us this product? And, I don't know the answer to that. It may simply be that this carbocation is more stable than this one because, remember, carbocations are sp2 hybridized, which means that this wants to be that bond angle, that bond angle, that bond angle. These all want to be at 120 degrees. And remember, the chair cyclohexane is very stable where all of the bond angles are at 109.5. So remember, these bond angles here are 109.5. That's the ideal tetrahedral bond angle. But if we make a carbocation, let's just have our hydrogen coming out here, we are no longer talking about a tetrahedral position. We're sort of forcing this into a trigonal planar geometry which in a cyclohexane may not be an ideal geometry, whereas with this one, this carbocation here, you can still have your nice chair cyclohexane, and then this carbocation can be coming off here, and these bond angles can exist in the ideal 120 degrees. And then it may just be that this hydride shift is relatively easy to happen because of that geometry.